Okay. Thank you. This is the last presentation. I will try to be short, to be in time. First I want to acknowledge my co-authors from University of Naples, University of Partenope, and MAPEI. In this work we will talk about the use of FRP to increase the deformation capacity of columns or the shear capacity of columns. As discussed this morning, RC buildings are vulnerable to seismic action, as demonstrated clearly by last earthquakes. But now FRP is a material which is really most used in structures. This is an interesting picture from the Amatrice, which is the epicenter of the last earthquake in Italy. This is a building which was made by two parts, one part of masonry, one part of RC. So the masonry buildings collapsed completely. This is the RC building which was strengthened by using FRP, and there is no damage on this part. So this is just to tell you that FRP is now a well-known technique, and it is really used on RC buildings, and it is also effective. What we want to see now is something about the theoretical formulation. We really know that the use of FRP could be effective to increase ductility and shear capacity, but the focus of our work was to try to give an answer to these two questions, which are how we can compute the ultimate drift when we use confinement, and how much is the accuracy of existing formulation to predict the shear capacity of FRP strengthened members. To give an answer to these two questions, what we are doing in Naples is to carry out a series of experimental tests on RC columns, both governed by flexure or shear, which means slender or short columns. These are what I will show you here is just the preliminary results of this experimental program. We have now already tested 3 flexural governed columns and 3 columns governed by shear. The reinforcement is obviously different, because in this case we want to attain the flexural failure, here the shear failure. So here we have obviously a big amount of longitudinal reinforcement, while the stirrups are poor, and exactly the opposite in this case, as well as the shear span is different. Here is 5, while here is 3. What we did is to strengthen the flexural governed columns by using FRP at the zone of plastic hinge for a length of 50 centimeters, while we use strips of FRP to increase the shear capacity of these columns. We have 3 tests on flexure, 3 tests on shear. We have 2 concrete material properties, and FRP strengthening solution made by 1 or 2 plies of FRP layers. So this is the test setup. Obviously, this is to apply the axial load. We have a constant axial load of knee equal to 0.1, which means the normalized axial load is 0.1. This is the actuator to provide the horizontal cyclic displacement, and obviously what we did was to apply horizontal displacement in cycles by increasing the displacement. This is the flexural column, and this is the shear one. Okay, let's go throughout the experimental results. This is a summary of the preliminary results on columns governed by flexure. As you can see, this is the force displacement relationship for the as-built specimen, while these two are the curves related to the FRP strengthened specimens. You can see obviously that when we use FRP at the base of the column, the ductility is strongly increased. And if the quality of concrete is the same, the strength is not affected by the FRP solution, obviously, because this is just confinement. In this case, we use 2 layers of FRP. The quality of concrete is higher, so there is a change in terms of strength, but obviously also in this case we had much better behavior in terms of ductility. As concerns the failure mode, obviously we had the classic inelastic deformation at the base of the column in the case of as-built columns, while in case of FRP there was a crack due to the crushing of concrete, internal concrete. So what I have reported here in this slide is what we recorded in terms of strain on the FRP. As you can see here, we applied in the zone of plastic hinge where we applied FRP several strain gauges at 3 levels, bottom, medium and top level of the FRP strengthening solution. And here you can see the plot about the readings of strain gauges from top, medium and bottom part on side A, C, B and D. This is the load direction, so obviously as we can expect, the compression is here or here depending on the reverse cycles of displacement. So the maximum strain were recorded on these two sides of the column, while in these other sides the strains were very low. What we have here is the ratio between the strain recorded on the FRP divided by the ultimate strain of the FRP. So what we can see is that on average, even when the displacement was a high level of displacement, the strain in the FRP was on the average about 30% of the ultimate strain, and then the maximum value were reached on this side when concrete started to push FRP because the internal concrete crushing was attained. While on these two sides, obviously, the strain were lower than in the other two sides, and this tells us that the strain profile are strongly non-uniform around the FRP. This is the same graph but related to the specimen strengthened with 2 plies. Again, we have more or less the same thing. The average strain is 30% of the ultimate strain at failure, while a peak of 40–50% is achieved in this part and on the strain gauge in the side C. Okay, this is the comparison between the envelope curves. Here we have F divided by F max, just to compare the 3 specimens, even if the concrete compressive strength of this specimen is higher than in these cases. What we can see here is, by this table, is that obviously we increased a lot the ultimate deformation capacity. We move from 6.4 up to 10 in specimen with 1 ply, or 9 in specimen with 2 plies. I remember you that here the concrete quality is different. So obviously, as expected, the concrete wrapping at the base was able to significantly increase the ductility of our member. But our question is, are we sure that we are able to predict the ultimate drift capacity by using available literature expression? To be honest, just in Eurocode 8 we have an expression which gives us directly the possibility to compute the ultimate drift. You know, in the FIB, CNR, ACI code, so other literature available international guidelines, we just have provisions related to the increase in terms of concrete strain. And this is the reason why the predictions are not always so good. So if we compare what we can obtain by using the available expression, this is the Eurocode formulation, and in this case we can directly compute the ultimate drift by inserting the FRP contribution, which is inserted in this expression here. And in this case we have a quite good prediction with respect to the experimental results. While if we use the provisions given by the Italian guidelines, for which it is possible to compute the ultimate concrete strain increase by using FRP, and then you need to compute the ultimate curvature increase, and then you can compute the ultimate drift by using this formulation. So you cannot compute directly this term, but from this term you can go to this term. In this case, the results are not so good because the theoretical drift is higher than the experimental one. And the same thing happens if we use the FIB bulletin provisions, if we use the version of 2001. Again, we have that the prediction are not so good. What about ACI? If we use ACI, again, the code give us provisions about the concrete ultimate strain, and then we need to pass from this formulation, and in this case the prediction are too conservative. So as a conclusion of this first part of the presentation, we can say that confinement is well known, which is effective to increase the ductility capacity, but there are several formulations to compute the benefit in terms of ultimate concrete strain, while just aerocredate give us a formulation to predict the ultimate drift, which is what we need when we perform a pushover analysis and when we try to model an airside building, considering the effect of FRP wrapping. So it is obvious that probably in the future it is necessary to have to focus on the formulation related to the ultimate drift capacity. Coming back to the second part of our work, which is the shear capacity increase by using FRP on short columns. Here, very quickly, I want just to show you what happened in our tests. This is the comparison between the experimental behavior of short columns strengthened with FRP with respect to the shear capacity of the column without FRP. What we had was a very significant increase by using one ply of strips, discontinuous strips. The increase was about 80% in terms of strength and 100% in terms of ductility, even if the behavior was brittle. The failure was brittle, not that high. Why? When we used two plies, we were able to change the failure mode from brittle to ductile once. And again, we attained very interesting results in terms of strength and ductility increase. So, even in these tests, what we are doing is to recording the strain on FRP. We really believe that this is a very important issue for us and for the scientific community in order to calibrate reliable theoretical formulation to predict the shear strength increase and also the deformation capacity increase. What we have in this case is that on average the ratio between the strain recorded on the FRP divided by the ultimate strain of the FRP ranged between 30 and 50%. The maximum strain were achieved on the second and third layer of FRP, and the maximum strain were recorded in these sides. Exactly more or less the same thing for specimen S3, which was strengthened with two plies of carbon fibers, and again the maximum value were in the range of 35-50% with respect to the ultimate strain. Even in this case, if we compare the prediction in terms of FRP contribution to the shear capacity, we have very large variation. And I have to tell that also the formulation available in literature to compute the shear capacity of RC members without FRP, they also provide very big variation. So what we have is that if we compare the theoretical prediction with the experimental result, we have really conservative prediction, and in several cases also very large variation between the theoretical results and between theoretical and experimental results. So again, probably even if shear strengthening is clearly effective, we need to focus in the future to try to find a unified approach in several international guidelines to reliable predict the shear capacity increase by using FRP systems. And thank you for your attention. This was my last slide. I hope I was in time.